After that brief introduction to vectors, let's now move on to the next topic, which is force. And now, force, as we generally understand, is a physical entity which leads to change in the state of the system, and in mechanical terms, it basically leads to motion it basically leads to motion of the system or particle or mass or whatever is under consideration. Okay. Now, we are all aware of various kinds of forces. We have seen their manifestation in our day-to-day life as well as you have learned about them. For example, if you throw a ball upwards, then the ball will keep going up. It will, of course, not continue till a long time. It will reach certain height, stop there momentarily, and then start falling back. And that is all because there is a force of gravitation, right, or the gravitational force. So the body is under the influence of force of gravity. Right? Similarly, if you kick a ball on the soccer field, then the ball may roll down on the pitch till a certain distance, and then without anything else happening, it slowly comes to a halt. And that now is because of the force of friction, or whatever we call as force of friction. Right? Now we can take several other examples of this. For example, if now we go to more academic examples, then two negatively charged particles, for example, let's say electrons, if projected towards each other, then they repel each other, and we know that because of the electromagnetic force, and like charges repel and like charges attract and other things. And of course, we will encounter more examples of this force later on. So, intuitively, we understand what force is, right? And we also use it in literal terms to explain resistance, or the effort that one needs to put in and all that, right? So we have some intuitive understanding of the force. And now what happens is, fundamentally in nature, there are only four forces. So let's say I can call fundamental forces, right? And in nature, there are four types of fundamental forces. Okay. Again, the first two everybody has encountered as well as is aware of. So, the first is gravitation, second is electromagnetic force. Now, there are two more forces. One is called the strong or the nuclear strong force, and the fourth one, last one, is the nuclear weak force. Right? And of course, their strengths are different, and we can have a comparison of their strengths and all that, which we are not bothered at this moment. But there are these four fundamental forces. Right? Again, they have some peculiar properties. So, the force of gravitation and the electromagnetic force, these are called long range forces, or actually, in principle, they are infinite range forces. So that means all bodies, massive and charged, are under the influence of force of gravitation and electromagnetic interaction. Doesn't matter how far apart they are, there will be some influence of this. On the other hand, the strong and the weak force, these are short range forces, and the range is so short that only at subnuclear level one has to worry about these forces, right? So that is now the obvious reason why in a course on mechanics or extreme magnetism, we are only interested in the first two forces, and we rarely encounter or really talk about the other two kinds, because then they are in the realm of nuclear physics. Okay, so we will sort of remove them from here, and then we'll discuss. Again, we are not interested in the properties or in the true nature of how do you understand the force of gravitation, or what is the electromagnetic force, what leads or what generates these forces and all that. All we are interested in is understanding how the state of the system changes if it's acted upon by certain forces. Right? Okay, so we can do that. And now again we can say that no, you have listed only 4 of these forces, whereas we encountered several others. For example, everybody when we are walking or when we are driving, we always know that there is an air drag or there is a friction. So this is a force. And then what is the nature of this force? It's not because of gravity. No, I am not charged, or the air particles are not charged, or the ground is not charged. So it's probably not also electromagnetic, right? Then maybe this is also a different kind of force which we have not listed down here, right? There could be other examples also, and we will see what are the different examples. However, what turns out is, if we look at these forces carefully, right? And again, this is not part of what we are interested in, but just to complete the picture. It's an electromagnetic force, right, which is the most, let's say which is the most common type of force in nature, at least in terms of its manifestations, and where all we see is friction. So friction is manifestation of the electromagnetic force. Viscosity is manifestation of the electromagnetic force. What else we can have here? Normal reaction, which we will soon see in the next example. Normal reaction, this is also a manifestation of the electromagnetic force. So, of course, although these forces seem to be, or in mechanics we take them as different forces, we don't mix them up. We can see that these all come from the fundamental forces and mainly the electromagnetic interaction, which leads to friction, viscosity, normal reaction, and there could be other manifestation of this. Okay. So with that, now let's move on to what we are interested in is looking at how the force affects the state of the system, and this is normally termed as equation of motion, right? So basically what we are interested in is looking at the equation of motion of the particle or the system under consideration. And in this aspect, of course, the Newton's laws of motion are the guiding principle behind this. What we say is that a body acted upon by an external force, and now it's extremely clear here that force is a vector quantity, so we'll write it down as a vector, right? The mass of the body is m, and the force applied is going to be directly proportional to the acceleration or the change of state of the body or the system, right? So F equal to ma, that's a standard equation which again you all have seen at some point of time, and we can write this down in differential form and write down acceleration as the second derivative of position, time derivative of position, so m d2x over dt square. So that is our equation of motion then, right? And now, so now from here, what we develop is, since we said that the force is a vector quantity, right? That means if a body is acted upon by several forces, right, in different directions, then the total force, we'll call it F net, the total force on a body which is acted upon by several forces in different directions will be, let's say I equal to 1 to n, there are n forces, will be the vector sum of all these different forces, right? So forces have to be added vectorially, and the resultant vector is the one which will govern this equation. So the direction of acceleration, net acceleration, will be in the direction of net force, and the net force is going to be the vector sum of all the applied forces, right? And in principle, the entire equation of motion of the body is included in these two equations. We can find out, if we know about the system and the applied forces on it, we can calculate the net force using laws of vector addition. And once you know the net force, and if you know the mass of the body, then we can find out its acceleration. Okay. Continuing this a bit more, we can again write the same things in terms of let's say statements, right? And the two statements that we make out again, just to clarify the point more, are all forces, right, whose vector sum. So let's say a body applied by multiple forces. If the vector sum is equal to 0, right, then state of the system which is acted upon by these forces will not change. Right? So state of system can only be changed if there is a net force on the system. So if it has multiple forces whose vector sum is equal to 0, then the state of system will not be changed. Right? Or so for example, if we take a solid object in this particular as a system, then if you apply multiple forces on it and the total net vector sum of this is 0, then the object will be simply stationary. It will not move or it will not change its state. Now, related to this, the second statement that you can make is any net force on an object or a system, right, will lead to motion of the object in the direction of F net, right, which is the vector. So whatever is the net resultant force, the object will start moving in that direction, and when I say motion, it basically means acceleration. You can find out the acceleration. Once you have the acceleration, using the relation between acceleration and velocity and position, we can find out the actual state of the system, which is acted upon by this force. Okay. So with this, let us now look at the solution of the equation of motion for different systems by taking a few examples. Right. Let's do that. And we'll start with the most simple system. Right. So first of all, since we said that force is a vector, what we'll do is we will fix our coordinate system. Right. So for example, this is my XYZ coordinate system. So this is X, this is Y, and this is Z. This is my origin, right? And now let's take a very simple system, object of mass m or a body of mass m resting on a table, right? So I can sort of draw a table here, right? And then, of course, the table, so let's say the table plane is in XY plane and it's standing along the Z direction, so that the Z becomes the direction of gravity, right? And let me put a mass m on this table, right? So it can be anything. You can keep a mobile phone on the table which normally does not move, or you can have a teacup kept on the table and it does not move. So this is the mass. And now since it is stationary, can we write down this equation of motion, right? So yes, we can. And what we do is we simply write down the equation of motion as F equal to m, which is mass of this thing, and A, right? And A is a vector. Now again, since F is a vector, we can also write it down in component form, just like we can for any vector. So in this coordinate system, we'll write down F into its component form. And now, looking at the system or whatever information we have about the problem at hand, all we have to do is find out Fx, Fy, Fz, right? And from there, we can find out the acceleration in different directions. So let's now look at it. So of course, everybody knows that, or we all have knowledge that if something is stationary kept on a table, right, then there is actually no net force along the x direction, y direction, because actually we don't even have anything which is applying force in the x or y direction. All we know is gravity, which is all pervasive, at least on Earth, and that's acting in my coordinate system, acting along the z direction. Right? So what I can do is, looking at the problem, I can say that fx is 0. Okay? Similarly, fy is 0. Right? And now what about fz? So for fz, I know that gravity is acting downwards. It always acts downwards. In fact, gravity is the one which gives us a sense of up and down. So gravity acting downwards. The mass is resting nicely on the table, right? And it's not falling down. That means something must be keeping it on the surface, and that something is called the normal reaction, or the N. So, in that sense then, Fz in k cap direction, right? So Fz k cap is normal reaction, which is pushing it upwards, minus mg, which is pulling the mass downwards in the k cap direction, right? Okay. And now here, now we have to, since we are dealing with vectors, we also have to, and along with the coordinate system and reference and the origin reference, we also have to have some sense of positive or negative direction, right? And the way we, and of course the sense remains arbitrary, completely arbitrary. However, normally what we say is, on a abstract coordinate system, positive x-axis, positive y-axis, positive z-axis is the positive direction of motion, and negative x-axis, y-axis, z-axis is the negative direction of motion. So that means gravity is pulling you down, and we get, so in this particular problem we are saying that downward direction is negative direction of motion, upwards is the positive direction of motion. So the normal force is a positive force because it's pushing it up. The gravitational force is a negative force, it's pulling it down, and the net force in the z direction or in the vertical direction is normal force minus the real force, and the k cap will be represent the direction, right? Now, if one says that since the mass is stationary, that means the total F on it is 0, right? And which is also same as ma. We think the acceleration is also 0. If this is given, because we know that the object is not moving, in that case, if F net is 0, then all the three components of F have to be 0. Fx we all know it's 0, Fy we know it's 0, and from the condition that the mass is stationary, we have to have Fz also equal to 0, sorry, not the bar, just the component Fz equal to 0, and this implies that N equal to mg. So for a stationary object resting on a surface, the normal reaction is equal to or will be balanced, or the gravitational pull will be balanced by the normal reaction. Right? A well-known result. You all have done these kind of problems. Nevertheless, it's a good starting point while considering equation of motion of different systems. Okay. Now, what we can do is we can modify this problem slightly, and now I can say that okay, so fine. So my mobile phone was sitting nicely on the table, or my coffee cup was sitting nicely on the table, and what I started to do was, I started to push it. Maybe your friend wanted the coffee cup, and then you simply pushed it in the direction of your friend. Right? So that's a force applied on the system. And now, of course, your intention is for the cup to move. That means it has changed its state, right? And now can we sort of analyze this problem? Yes, we can do this again. We start with our component form of the force, net force. Now, let's say for time being, you are when you are sitting here and your friend was sitting somewhere there in y direction, right? So the force need to apply the object need to move in y direction. So in that case, as the problem says, what you are doing is Fx still remains 0, right? Fz is still n minus mg, right? And of course, since the cup is not falling down, we'll see that to net Fz is 0, so n minus mg n equal to mg. And now Fy is the force applied, right? because this is the force that we are applying in y direction. So Fy is force applied. We'll make the problem slightly more realistic. We know that no surface is frictionless. So let's say there is friction in this, right? And and friction always opposes direction of motion. So the object will also be under the influence of force of friction. As soon as we start applying force to move it, friction will try to stop it, right? And then again, positive y direction, positive force, negative y direction, the friction force, and the friction force is equal to mu n, where mu is the coefficient of friction. So I am using these terms without explaining much because we all have encountered them previously in our earlier courses, right? So anyway, so Fy in the direction of this is F applied minus mu n, right? And now my force equation becomes F vector is, well, Fx is 0i, so Fx is 0i plus Fy is F applied minus mu n in j cap direction, and Fz again is n minus ng, but we know that it's not falling down or going up, so that is also 0k. N will be simply equal to ng, right? So this is my force equation, and that means from here I know that acceleration will be in y direction. Since there is no x component of force, there won't be any acceleration in x direction. Net force in y direction, in z direction is 0, so there won't be any motion in z direction. Acceleration az will also be 0. Only thing that remains here is this. So we can write it may j cap is equal to F applied minus mu n j cap, right? So this is my equation of motion for this particular problem, right? And now what we can do is we can have more information regarding the system and then further analyze it or get a result. For example, if one says that you try to push the cup but you are not trying hard enough and then the cup doesn't move, so even if you are applying some force, the cup doesn't change its position, in that case this is equal to 0, and what that means is that the applied force is equal to the force of friction that is acting on the cup, right? So as long as this condition is satisfied, and if we try to generalize this, then basically this condition, if this condition is satisfied, that is, as long as the applied force is less than the force of friction, right, the cup will not move, right? And we all know that that is the true case, and that means there won't be any motion in the y direction, and the overall system will remain as it is, right? Again, if you apply a force which is larger than force of friction, then the particles simply start moving in the other direction. Okay. So this is one example, simple example, but basically to give an idea that what kind of information and what kind of analysis we are interested in while working with systems in motion under force.